Okay, welcome everybody to KETIV Virtual Academy. My name is Christina Ung. I'm on the marketing team here and I help facilitate these sessions. We're excited that you're here and we hope that you're enjoying KVA. Today we have Snigdha Sarkar joining us as our host, and she's going to be talking about electronics thermal simulation using Ansys Discovery. At the beginning of the month, you should have received a newsletter that covered all of the upcoming sessions for this month. And we will be sending out one in the beginning of October. But you can always check out upcoming sessions on this link, ketiv.com/KETIV Virtual Academy. Be sure to check it out to stay informed. Next week, we're going to have Jose Paredes Clara on, and he's going to be talking about managing change orders in Fusion Manage. Thank you again for joining, everybody. Please be sure to check out all of our other resources on our website if you're needing more help with your simulations. We have a lot of free resources. Let me drop the link in the chat here. And yeah, be sure to leave your questions in the question box. And at the end of the session, you will also have a link pop up on your screen to leave us feedback. Let us know if you enjoyed the session or what other topics you'd like to see covered. Okay, and I will let Snigdha take it away. Thanks again for joining, everybody.
Thank you so much, Christina. Hi, everybody. My name is Snigdha Sarkar. I'm Simulation Practice Lead here at KETIV. Welcome to today's KVA session. Like Christina mentioned, we're going to be talking about electronics thermal simulations in Ansys Discovery. For today's agenda, we'll talk a little bit about how Discovery is uniquely suited to meet some of the simulation challenges that we see today in conventional product development workflows. We'll talk about some of the capabilities that differentiates Discovery from other simulation products in the market. And then we'll also go through some commonly seen industrial examples where Discovery can be used for thermal simulations. Lastly, we'll cover everything up with a demo of an electronics enclosure wherein we'll do a fluid/thermal problem in real time. Like Christina mentioned, if you have questions, feel free to leave that in the Q&A box. I'll take the questions towards the end of today's session. So if we look at conventional product development workflows, the way we usually follow the steps are outlined here in this chart on the left. We'll start with conceptualizing the design, which may be based on hand calculations. It can be based on empirical data, legacy designs, etc. We'll do some preliminary design work. When we get to the details stage just before prototyping, we'll probably use simulation. But when you use simulation at that point, what you're doing is you're trying to validate your design to see that it meets design goals and requirements. But truly, you haven't done simulation-driven design. And it's a missed opportunity because imagine being able to leverage simulation early on in your workflow when you're in the conceptualizing phase. If you can use simulation to give you confidence on selecting the right design parameters or configuration, you'll have much more success in the downstream steps of this workflow. And we've noticed traditionally in the industry, when you start making changes to your design, in the latter stages of this workflow, it is that much more expensive, that much more time consuming to go back to the drawing board. So you should rather, try to get your design right the first time. And that is what Ansys Discovery can help you do, not just for those people who are, full-time analysts, but also people who are design engineers and just want some good guidance on what the design direction should be. Now, we've done a couple of KVAs on Ansys Discovery. We'll keep doing more sessions in the future because it's such an exciting product. But for those of you who are new to Ansys Discovery, just to give you a brief overview of what it really is, Discovery is a simulation-driven design tool that combines instant physics and high fidelity simulations alongside interactive geometry modeling in an easy to use interface. I think it's one of the only simulation tools out there that can handle so many different physics under the same umbrella, alongside being able to change your design on the fly and see how that impacts your simulation results. My background is in computational fluid dynamics, so I often use it for fluids and thermal analysis, but the rest of my team members use it for structural and electromagnetic analysis as well. If you're interested in seeing more webinars or sessions from us on these other topics, feel free to let us know in the comments or in the feedback, and we'd be sure to follow up. Now, talking about thermal applications, I wanted to cover, some commonly seen industrial applications and highlight how Discovery can be used for those problems. So say, for example, if you talk about HVAC, heating, ventilation, and air conditioning, low-hanging fruit, commonly done in almost all industries. We see a lot of customers from the commercial space and even healthcare space where air quality is important, thermal comfort is important, maintaining negative pressure rooms are important. And in those cases, when you're doing, quick and dirty analysis, preliminarily to understand what should be the optimum design configuration, Discovery is the perfect tool for that. You could, optimize your flow path, minimize pressure drop, identify hotspots, reduce overall temperature, look at thermal gradients, identify, low circulation zones or recirculation zones. Over on the right, you see, some graphics wherein we have an original duct design. And we solved this in Discovery, saw, recirculation patterns over here. We were quickly able to add some guide vanes, and then the flow becomes a lot more well-behaved. And this particular modification is so easy and so quick to be done in Discovery that there's no reason you should not be leveraging Discovery's capability in doing things like this. Similarly, if you look at heat exchangers, CFD/thermal analysis for heat exchangers can range from simple to very complex. But when you're just starting off with your design, you have some major design changes to make. You want to make sure that your heat transfer is maximized, is most effective. And if you want to try out different permutations and combinations of design, Discovery is the perfect tool. Again, you can optimize the flow path, you can look at component placement, you can even do, additive manufacturing type simulations and topology optimizations to see what kind of surface area works best for your heat transfer goals. So definitely another area where Discovery is commonly used. Internal combustion engines in automotive industries, anytime you're trying to design the cooling package, exhaust systems, radiators, etc. Definitely Discovery can be leveraged for minimizing pressure drop, optimizing flow path, and reducing temperature. And lastly, the main topic for today's KVA, which is air-cooled electronics, doesn't really have to be air-cooled, could be liquid-cooled as well, as long as you're not doing phase change, for which, there are more flagship products that are better suited. But if you're doing electronics thermal applications, whether it's just a standalone solid body with a convective heat transfer coefficient, or if you want to do conjugate heat transfer, coupling fluid and solid heat transfer, all that can be done inside Discovery. That is the demo problem that we've selected for today's session. But most commonly in this space, Discovery is used for heat sink optimization, fan sizing placement, ventilation sizing and placement, and component placement. Because it's so easy to change the geometry on the fly, you'd be able to look at various permutations and combinations of your design and see which one works best for you. So with that said, let's jump into the demo. And I'll start with the problem statement slide and then switch to the GUI. But this is basically an electronics enclosure over here. And what I'm going to do is I'm going to create a watertight enclosure around this and assign some heat loads and some fan velocities to see how the flow propagates in this particular domain. And then we'll see what kind of post-processing results we can get in Discovery. Again, if you have questions, feel free to leave that in the chat box. I'll definitely get to it later on. Okay. All right, so let me go ahead and share my Discovery session. Christina, do let me know if I'm sharing the wrong screen by any chance, but I think I should be sharing. Okay, great. Excellent. All right, so this is the electronics enclosure box that I was showing in the slide. I'm using the latest release version of Ansys Discovery, which is 2024 R2. I'll quickly walk you through the structure tree over here to describe what we're seeing. Basically, we have these two PCB assemblies that are, being highlighted as components over here. We also have two power supply blocks, these two guys. And then, we have the fan components over here. And lastly, we have this enclosure, which, as you can see, is obviously not watertight. It's not closed. At the top and also here at the bottom, if you look, there are a lot of nooks and crevices that are open. So if I was to try and manually fix all these open areas, it would be a bit tedious and time consuming. So what I'm going to try to do is create an enclosure manually. It's simple to do. If you have IcePack, which is another Ansys thermal CFD tool in the electronic space, you could also, just quick scope your geometry to identify components that can be easily converted into IcePack components. If you're interested in a KVA session that shows you that process, do let us know. We'd be happy to cover that. But in today's example, I'm going to do it manually. I apologize. Give me 1 second. Okay. All right. So we have this component over here. What I'm going to first of all do is create a new component. The moment I create a new component, my parent assembly, grays out. And that's because whatever modification I'm going to make, I don't want it to interfere with my base geometry. So that's why, I've created a new component. If I look at this geometry head on, I can go ahead and create a sketch on this bottom surface over here. This is the base of my electronics box. And what I'm basically going to do is create a rectangle that approximates the shape and the dimension of the enclosure that I'm trying to create. It doesn't have to be super exact because you can later adjust the box to match the edges of the actual enclosure. But you can just eyeball it and create a rectangle over here. Once you do that, you can go back to the solid mode by clicking on D on your keyboard. That's the hotkey for toggling to the solid or 3D mode. And you'll notice that there is this lavender surface that now shows up in my structure tree. So I'm just going to go ahead and pull this surface up to the top of the enclosure. So you could select a face, or I'm going to go ahead and select the edge. And this creates an approximate box that encloses everything within my structure tree. Okay. I can go ahead and make this translucent so that you guys can see what's happening inside. And once I've created this box, I need to subtract the solid components that are enclosed within the box, because the remainder will be the CFD domain available for my airflow, correct? So let's go ahead and do that. In order to do that, I'll first of all activate my parent structure tree so that all components are available for operations. And I'm going to use this intersect tab over here, which we can use to perform Boolean operations. The combine tool can be used to merge bodies, subtract bodies. So let's go ahead and use that. The good thing about Ansys Discovery is that it's highly interactive. Every time you select something, you'll usually get prompts on the bottom left corner. You can follow those prompts in a step-by-step fashion. And even without, looking up a user guide or manual, you should be able to follow things through. Basically, this is asking me to, select a target object and then subtract the objects that I want to from the target object. So my target object is this fluid volume, and I want to subtract the power supply boxes from it. Notice that even though my mouse is hovering over one of the boxes, the other one also gets highlighted in yellow. That's because these are copy of components. So instances that are created by copying one component to the other, those associations are maintained throughout. So whatever function you're performing on one instance of the component gets mirrored in the other instance of the component as well. This is an easy way to reduce the number of manual steps you need to complete in order to clean your geometry. So both the PCBs, all the fans, both the power supplies, they're all instances, and we'll see that it's easy to make your overall workflow efficient by creating these. So I'm going to go ahead and subtract them from the target body. And let me see, 1 second. And when I do that, hopefully, you should see this subtraction over here. So those bodies were taken away from this larger fluid enclosure that we are trying to create. The next order of business is to subtract the PCB assembly from the fluid enclosure as well. Again, I'm going to go ahead and follow the same steps, select the target body, and then select the cutter body. Because these are instances, both of them get subtracted at the same time. Okay. So you can see the negative volume being created. Now, we can do that for the fans as well, but if you look at the fans over here, they're a little bit more complex than I need in my overall thermal simulation. I don't need so much detail in the CAD. I want to simplify the fans before I go ahead and subtract them from my overall fluid enclosure. So the way to do that, and an easy way to do that, is to open any one instance of this fan component in a separate tab. My original session is still active over here, but this tab over here is just an additional window that opens to work on a specific component. And we're going to repeat similar steps as the main session over here, wherein we're going to create a new component. You'll see that the base geometry gets grayed out. And we'll go ahead and create a sketch on this fan face as well. This is to, again, simplify the fan geometry a little bit. You can see that there's a shroud around the fan, right? I'm thinking that maybe I'll just approximate the fan inlet face and apply a boundary condition on that. And maybe the shroud acts as a restriction, so I can just subtract it from the overall fluid domain as a solid body. So as I perform the steps, this will be more clear. Let me just go ahead and make an approximate rectangle over here. And then we can also go ahead and make a circle. And this is to, again, approximate the face that is allowed for fan flow to come in. If I go back to the 3D mode by clicking D on my keyboard, you can see that this is the kind of surface that was created, okay? Now what I'm gonna do is I'm gonna go ahead and pull this surface up to the back face of this fan body. So just click on any particular face and the extrusion is going to be aligned with that. And let us give this guy a new color so that it's a little bit more interesting. Maybe I'm, open on my other screen. So anyways, but basically whatever operations I've performed over here should be mimicked over here as well. So you can see this simplified geometry around the shroud copied in all the instances of the fans over here, okay? Once I've done that, I don't really need the fan anymore because all I'm going to do is separate the body I've just created from the fluid enclosure. So I can actually just go ahead and delete this guy. And so I'm just left with the approximation of the fan inlet area. Let us go back to this region over here. And now we can go ahead and subtract these fan bodies from the overall fluid enclosure, okay? So again, we'll do the same steps. Go to combine, select the target bodies, and then select any one. The rest of them get automatically subtracted, okay? So if I turn off the fan over here, you can see what the final fluid volume looks like. And if you want to see, a section view of the volume that we've just created, you can press X on your keyboard and move the grid a little bit to understand where the cavities are, okay? So this is what the domain looks right now. And what we'll do, just to make sure that we have a boundary condition available on the fan body, we'll go ahead and align this face with the intake face of the fan, okay? So let us pull this face up to this guy over here. So now you should be able to see more clearly exactly what type of domain we've created. We're going to assign intake fan boundary conditions on these faces over here. And then the inner solid volumes that we've been subtracted, they can be assigned a heat load. All right. Let's rename this as the fluid domain. And let's also go ahead and create an outlet. I'm just creating an arbitrary outlet. It could be a grill, it could be some other type of geometry, but this is just to show you guys. Just going to create a random opening over here. This is a surface in the structure tree. Let's just go ahead and project it. And you should see that outline on your original domain, okay? Now, the other thing that you will notice in the structure tree is there is this green crosshair next to your components. If you hover over it, it'll tell you that you can either include a component in your final simulation or exclude it. So I don't need any of these additional bodies in the simulation. All I need is the fluid domain. And then I'll keep the PCB assemblies as well so that I can assign a heat load to them. Okay, I want to assign a volumetric heat load to them, so I'm just going to go ahead and keep this in the simulation. So now geometry-wise, we have a watertight geometry. It was simple enough to create without having to close individual openings. You can assign name selections here in the model stage where we are cleaning the geometry, or you could also switch over to the simulation stage in the explore mode to assign some name selections and boundary conditions accordingly. So say, for example, you want to assign a boundary condition to any one particular name selection. You can highlight those faces or select those faces. On the bottom over here, you can come to name selection and give them some name. And then this guy over here in the back could be our outlet. This is just the name selection. We still haven't assigned any boundary conditions. But before we do anything inside your simulation mode, make sure that the material assignment is correct. Sometimes, we'll keep the default material assignment and it's going to give us error later on because the default material assignment is always structural steel and our entire volume is not made out of steel. It's filled with air. So that's what we need to assign. So what we're going to do is click on the actual volume from the structure tree. When you do that, the material shows up here on the right. You can choose any material from the Discovery library. It usually has an orange D right next to it. I also have other Ansys licenses for products like Granta, so I have a much more extensive library to choose from. But let's go ahead and just select air. And the moment you select air, you'll notice that the appearance of the volume changes somewhat. That is because, the appearance of air is differently stored inside Discovery. So that can be a good gut check for you to make sure that the right materials are assigned. Everything that's solid and still included in the simulation is still structural steel. Let's keep it at that. But if you wanted to go ahead and choose other materials, again, you have a ton of options over here, especially if you have things like Granta installed on your machine. If you go through the list, it's quite comprehensive. You even have PCB materials if you wanted to select that. But this is just for, showing you the process. So I'm going to keep it at structural steel. Once I do that, let's start assigning boundary conditions. The first thing that I'm going to do is I'm going to go ahead and assign some thermal boundary conditions for the heat load in this particular problem. On the top, you can see the different types of simulations you can run. Electromagnetics on my machine is blanked out because I don't have the electromagnetics tools installed, but the other things are available and they are active. So let's go ahead and do that. At the moment you click on any one particular type of simulation, you'll see a couple of different options pop up on your screen. You can assign an insulated boundary condition or a heat load or a particular convection boundary condition with a heat transfer coefficient, or you can also go ahead and assign a temperature. Right now, we are going to assign a heat load. So what I'm going to do is I'm going to select the two volumes in my structure tree and assign a total heat value to these two bodies. You could also go ahead and assign a heat per unit volume if you wanted to. Right now, I'm just going to go ahead and hit enter. The moment you do that, you will notice a couple of things get populated on your screen. Over here at the bottom, under the structure tree, you now have your physics tree. This has your materials, this has your boundary conditions, this has your connections. And Discovery is very intelligent. It is able to detect a lot of the boundary conditions automatically based on the inputs that you've selected. So say, for example, when I assigned a heat load of 50 watts, it automatically chose the non-slip walls in my problem. It also decided to, establish the fluid-solid interfaces in my problem. So say, for example, if I hover over the fluid-solid interfaces, it knows exactly which faces act as the interface between the air volume and the structural steel volume in my problem. Okay, so you see that highlighted in pink. Somebody has mentioned, covering natural convection if possible. We can definitely do that in a separate session. One thing I will say is for natural convection, you wouldn't go with constant values of air density. Right now, I had chosen a standard constant value of air density because, this is the problem that I'm choosing to highlight in this KVA. But we can definitely do a buoyancy-driven problem the next time we meet for a discovery thermal session. And as long as you have that sort of setup available, you can easily do buoyancy-driven or natural convection problems in there. Right now, we're doing forced convection with fan flow. But great suggestion, and we'll definitely take that into account. All right. So once we've assigned the heat load, let's go ahead and assign the flow boundary conditions. I'll show you two ways of doing that because this is a newer feature, I think, that was added recently to Discovery, wherein you can associate your name selections with the boundary conditions that you have to assign. That way, you're not having to manually select surfaces. You can just tie it all to the name selection you've created. So let's go to fluid flow. And instead of a flow boundary condition, I'm going to go ahead and choose a fan boundary condition because I have my fan face set up accordingly. Now, there are other boundary conditions available to you. You can obviously supply wall boundary conditions, also porous zone conditions, also rotating fluid zones. So say, for example, you wanted to do a moving reference frame kind of a problem inside Ansys Discovery. That is possible as well. You don't necessarily have to go with the fan intake boundary condition. You could retain the blade surfaces and then create an MRF zone around it, just like you would in others' flagship CFD problems. For the sake of time, I'm choosing the simplest option right now. So let's go ahead and choose a fan boundary condition. And we'll click on this orange arrow over here. It allows you to choose name selections to be linked to the boundary condition. When you click on that, you can go ahead and select your fan intake. Select on this orange arrow one more time. And now you can see that whatever assignment you make will be allocated to the orange surfaces. Good thing about Discovery is it also has a lot of inbuilt fan libraries. So say, for example, if I had to choose one from Discovery, you can look at the information over here, what's the manufacturer, what's the outer and inner radius. And if you click on these tables over here, they come populated with, a dP versus velocity curve or dP versus, volumetric flow curve. You can obviously go ahead and create your own fan curve, right? If you have your own fan curve data, you can just go ahead and enter it over here. Add as many rows as you want. In my case, what I'm going to do is I'm going to go ahead and assign a constant pressure rise of 50 Pascal, okay? And so you'll see these pink boundary markers that indicate where exactly you've assigned your boundary condition. Now, another way to go ahead and assign your boundary condition is just directly selecting the surface. So say, for example, you want to assign a flow boundary condition. Instead of an inlet, you want to assign an outlet. You could just go ahead and choose this surface over here. Let's leave it at 0 gauge pressure and either hit enter or the green check mark. Okay. So whatever you've entered is all populated in this physics tree over here, your outlet, your intake, your heat load, and now we are ready to solve the problem. Keep in mind that we are in the explore stage, and this stage is really useful for making quick design changes and seeing how the results change. Why? Because the explore stage is using GPUs in the background to compute your solution. Okay. If you go to the refine stage, which is the last stage and the highest fidelity stage, the main differences are that, the mesh that you'll be using is different. You can use under the hood solvers like Ansys Fluent and Ansys Mechanical to run the same simulation, but you could also use something called the Live GX solver inside Ansys Discovery itself in the refine mode to both leverage GPUs or CPUs to get a solution. This can be useful for those people who don't have Ansys Fluent or Ansys Mechanical or other flagship products loaded on their machines. If you simply want to rely on Discovery for your simulation, that's possible as well. But in the explore stage, the kind of mesh that you use is a little bit different, and that is intended to give you faster results as you modify your design. The other thing that you'll notice is there is a fidelity bar over here at the bottom. This fidelity bar gives you control on how fine you want the characteristic mesh element to be in your problem. If you slide your bar towards the right, it's going to be a higher fidelity, meaning a smaller mesh size. So you'll be able to resolve more features in your problem, especially if the geometry is quite small. For the sake of time and speed, I'm just going to keep the fidelity at this particular location. And I'm going to go ahead and run the simulation over here now. And so you'll see that instantly the results start computing. We call this the simulation information display. There's a white line that you'll see that goes around the perimeter of this hexagon. The moment the simulation starts computing, you'll see this perimeter change into green, and that's when you'll see some values being populated. So just give it a second or two. And if you have any questions in the meanwhile, feel free to leave that in the chat box and I can get to it while the simulation is running. So you can see that by assigning few boundary conditions and making some modifications, you can get results pretty quickly. Obviously, these haven't converged yet. The way you notice whether a solution has converged or not is by looking at this legend on the right and making sure that the numbers are not changing anymore. So we'll give it a second to steady out, and then we'll look at more post-processing results. You could also look at velocity or pressure or vortices. Just give it a second to update. So you can see, the velocity looks a bit different. The contours have a few different settings. And you can go and look at the settings likewise. You can also look at the cut plane to understand the flow path lines a bit better. Let me show temperature instead. I think that is a little bit more colorful in this particular example. And then you can obviously move this plane wherever you are trying to get your results. Just like the move triad inside Ansys Discovery, this plane can be rotated, revolved, aligned with different planes. and you can look at how the solution is propagating accordingly. Let me turn the contours off so that this is a little bit more clear. And you can see that the numbers are changing slightly. If you wanted to go ahead and change this scale, you could just drag and drop the legend a little bit, and it will readjust the gradients accordingly. Or you could just click on any particular field and type in a value. So say, for example, if I type in 100, you'll see the color scheme change accordingly. And then you can obviously reset the values by clicking on this gearbox below. Okay. Now, the other really nice thing about Discovery is it allows you to create isosurfaces. So say, for example, I want to create an isosurface for identifying all regions that are above 80 degrees Celsius. And if I do that, I can quickly identify those regions that perhaps need a better heat transfer, correct? Similarly, if you look at velocity over here and I change, give it a second, I change this to a low value of velocity, say 0.4 meters per second. So you can see these are all the regions where we're not getting a lot of flow. And in this particular case, maybe that's just because I assigned, some random fan boundary conditions, which may not be suited for this type of a problem. But the idea is for you to be able to identify those regions that are probably dead. And, maybe you need more circulation accordingly. Okay, so let's go back to this guy over here. And we'll go back to the temperature over here. Now, there are some very exciting, features and capabilities that have been added to Discovery in recent versions. It is a rapidly developed tool with new capabilities being added every time a new version comes out. Previously, in the Explore stage, you wouldn't be able to look at a mesh or, assign local sizing. And what that meant was sometimes if you had wide range of characteristic lengths in your geometry, with the smaller features being extremely small, even if you shifted the fidelity bar to the extreme right, you wouldn't be able to resolve them. Okay, so now, Discovery has the flexibility of allowing you to assign local sizing even in the explore stage while you're using the GPU. So say, for example, I pause the solution for a second, and we want to look at the resolution of this mesh. Okay. Let me just go ahead and cut. Okay. So I've used a cut plane to show you the resolution in my mesh. I had not used a very high fidelity, remember, for the sake of, saving time and being able to show you real-time results. If I hover over it, you'll see the characteristic length is around 1.48 millimeters, okay? So that means that in the bulk zone, that is the smallest mesh resolution that you can get. So what if you have a feature that's smaller than 1 millimeter? And those are the regions that are not being resolved accurately, right? So if you turn on resolution alongside a cut plane, you can actually see which regions are not being resolved. They're highlighted in red. They have a very coarse mesh around it, okay? For the sake of saving time, I have a slide that shows what I'm talking about. So this is the kind of mesh that you get in explore stage. This is a voxel type mesh, different from the traditional tetrahedral or polyhedral type meshes you get for CFD. So say, for example, you don't add any sort of local sizing. This is the kind of coarse approximation you're getting. And that's fine. That might be okay for those regions that are not of interest and you don't want to spend too much computational power in computing those solutions. But if you have an area of interest where you want more resolution, you can come and add a local fidelity. And that way your mesh is going to be much finer resolved in that particular location. And you can do all that within the explore stage itself. So the way you do that is you can basically go ahead and add local sizing. And let me just choose this particular guy over here. I can enter a value of 0.5 millimeters. And when I do that, you will notice this particular setting being populated in your physics tree. And instead of using the global sizing of 1.48 millimeters, for these particular faces, now Discovery is going to be using a finer mesh. So see how flexible it is for you to have control over resolution, even though you're using, GPUs to do your solve and visualize your solution real time. So that's the beauty of Discovery, that it really gives you the best of both worlds. And once you assign a local sizing, you can also go ahead and look at the mesh. It takes a little while for the mesh to compute. You can see again, there's a little bit of a lag, which is why I had a PowerPoint slide in there. But the beauty of, this explore stage is that, you can really play around with different sizing functionalities, okay? And lastly, before, I end this demo, I also wanted to talk a little bit about the refine stage, okay? The refine stage is the highest fidelity stage of simulation inside Discovery. Like I said, if you have a flagship solver license like Ansys Fluent and Mechanical, you can leverage that to run the same simulation. So you're getting Fluent's accuracy with a problem that's been easily set up in Discovery. But the other advantage of the refine stage is also being able to switch between using GPUs and CPUs. So say, for example, you don't have, a state-of-the-art GPU on your computer, and that makes you doubtful about whether or not Discovery is useful for you. Well, you have the flexibility of just doing things the traditional way. You can end up using a CPU instead of a GPU inside the refine mode. So you could just go that way, even if your GPU card is not that great. And the other advantage inside refine mode is you can specify a meshing method, and you don't have to stay limited to tetrahedral mesh. You can actually go for a polyhedral mesh. And the polyhedral mesh is going to be similar to the fluent meshing polyhedral mesh for those of you who are familiar with it. So it's the best in class. In fact, I have a slide right here, again, in the interest of saving time and being able to show you real-time solution. This is the polyhedral mesh that is generated if I solve the same problem inside the refined mode. Nothing else, same setup, same local fidelity that I assigned over here, and everything else has global sizing. And you can see that these geometry surfaces are a lot more well-defined than the voxel type mesh that we had over here. Okay, so these are some results that I showed you guys early on. But when I solved this case with polyhedral mesh, these were the results that I was getting. And you can easily switch between the two stages depending on which one you prefer. Okay, so I'll pause here to see if anybody has any questions or suggestions about future KV8 topics.
We don't have any questions from our friends on YouTube, but if you're watching this on YouTube and it isn't September 19th, feel free to leave a comment with your question and we'll get back to you.
Absolutely. So we plan to, introduce a lot more content on making simulation simple and speedy for everybody. And stay tuned for more such sessions coming up, wherein we show you how to make easy modifications, and the comment about doing natural convection problems is noted. We'll definitely either have a KVA or just a